cramps in my legs from sitting down. Another day. I need a blanket. Chilly outside. Okay. We're going to get right into 5.2, which is a little bit of a, when I first looked at it, I thought it seemed a little more overwhelming than it is. So basically, we're not learning any new concepts. We're just applying concepts we already know to a broader sort of situation. So we're going to be bringing in things like stating restrictions on the domain, finding x and y intercepts, a little bit of factoring, a little bit of synthetic division, a little bit of starting our chart when you graph of where things are going to be positive and where things are going to be negative. So all things that we've already done, but we're kind of wrapping them all up into a larger question with a very long solution. So this video will probably be a little bit lengthy because I want to make sure I go through the steps for graphing that will make your lives a little bit easier. And there are quite a few steps. Like it's a definite method, the way that you're going to solve these problems. But if you follow that method, it's not too bad. So a lot less overwhelming than when I first looked at the lesson. So take the time to go through it. Make sure you write down kind of the steps that are going on. My note's going to look a little bit different than the note that's posted online. I'm still doing the same examples, but maybe just the way that I'm explaining it might be slightly different. I have to explain it the way that I know best, I guess. Okay, so 5.2 is called rational functions. We've talked about rationals many times, the idea that a rational number is just something that can be written in fraction form. Well, a rational function is the same idea. It's in fraction form, but it's a polynomial on top of a polynomial. So again, the degrees will change. You could have a cubic over a quartic. You could have a cubic over a quadratic. You could have something that's linear over a quadratic. There's all different combinations, but as long as you have a polynomial, so that means there's some variable that's involved in the numerator and a variable involved in the denominator. In our cases, they're going to be x's, but they could be of different degrees. Okay, so the idea with a rational function, polynomial over polynomial. Some main things you need to know about a rational function. Whatever the domain is of your rational function is going to be always that it belongs to real numbers, and the restrictions are going to be whatever makes this denominator 0. You know that in rational expressions, much of like we did in grade 11, remember we stated restrictions on rational expressions in grade 11? This is the same idea. If the denominator equals 0, it can't exist. So we want to eliminate all those situations where the denominator, which I've called g of x, equals 0. So that's going to be the domain. And that's going to be important because we have to avoid those scenarios. Those are going to become asymptotes as we go down. Okay, zeros of this function are simply the zeros of f of x. Because the way you think about it, finding a 0, okay, is when y equals 0 or h of x equals 0. Well, if this side of the equation equals 0, 0 times this denominator becomes 0. So now you're just left with 0 equals f of x. So whatever the zeros are for f of x will also be the zeros of h of x. So both of these have a role. The zeros of g of x are going to be the restrictions on the domain. The zeros of f of x are going to be the zeros of h of x. Okay? Write it down, think about it for a minute. These restrictions here, I mentioned it already, are going to become our vertical asymptotes. So they're going to become the vertical dashed lines that we cannot touch with our function. Okay, so those are some important things. A couple things just to warm up a little bit. There is an A example in the note, but it's fairly straightforward, so I just wanted to look at B and C. If you're simply finding the domain and the x and y intercepts, then you can look at it in a very simple case. The domain on the rational function is the restrictions on the denominator. So basically, if I factor this denominator, it makes it much easier for me to see the restrictions. So this is a simple trinomial, two numbers that multiply to -4 add to -3, obviously -4 and 1. So the two restrictions on this denominator are that x minus 4 can't be 0 and x plus 1 can't be 0. Well, x minus 4 is only 0 when x equals 4. X plus 1 is only 0 when x equals -1. So those are the restrictions on our domain. These will also be our vertical asymptotes. There'll be a line right at 4 at x equals 4 and a line right at x equals -1, dashed line, become our vertical asymptotes. In terms of the x and y intercepts, you do exactly what you did in grade 9. If you're finding an x-intercept, you let the y, or f of x, equal 0. Again, anytime this becomes 0, 0 times the denominator, doesn't matter what the denominator is still 0. So we're only looking at the numerator equaling 0, in this case an x. So the intercept there is 0, 0. And it just happens to be in the situation where you're finding the y-intercept. If I let x equal 0 here, well, 0 divided by anything is 0. Okay, so it also has to be 0, 0. So this one has vertical asymptotes of 4 and -1, and an intercept of 0, 0. Only a single intercept. Okay, so you can kind of like work around. This is just like a warm-up. We're going to get into big problems today, but this is just sort of the warm-up to the lesson. If you look at this a little more in depth, you have a quadratic over a quadratic. Factor both of them. This one is a complex trinomial. Can still be factored. That's grade 11. It's actually grade 10 work. This is a difference of squares. Can be factored. The domain comes from the restrictions on the denominator. So x cannot be -2 in this case or +2 here. Okay, that means we have two vertical asymptotes, one at +2 and one at -2. And then in terms of your x and y intercepts, the same thing. If you're finding an x-intercept, you let y equal 0. This goes away. So what values make this 0? Well, obviously x equals 1. This one's a little harder to see, but you bring the 3 to the other side, it becomes negative. Divide by 2, you get -3 over 2. So you have two x-intercepts. To find a y-intercept, you let x equal 0. When you do that, put a 0 in for x here, you have a 3 multiplied by -1, which is -3. Put a 0 in for x here, you have 2 multiplied by -2, which is -4. -3 divided by -4 is just 3/4. Okay, so you have another intercept, this time a y-intercept, 0, 3/4. Okay, so this is just warm up. This is all stuff you should know how to do. Can you factor? And you better be able to factor super fast. You should be able to look at a question, factor it, no problem. State the zeros on the denominator. Those are restrictions on your domain. Okay, find the x and y intercepts. It's just a matter of plugging in. If you're finding an x-intercept, y equals 0. If you're finding a y-intercept, let x equal 0. Solve. Okay? Warm up. Review. Okay, that's all grade 10 and 11 information. Okay. Now, as we get into this lesson specifically, there's going to be some important things. The main ideas are that we need to find asymptotes and we need to find intercepts. Okay, both definitions you already understand. You know what an asymptote is, you know what an intercept is, but these are going to be the key values that will help us graph any function that we see, any rational function that we see. Okay, so what we're going to look at is 3 different types of asymptotes. Okay. Okay, we're going to have 3 different kinds. The first one is a vertical. Okay, I'm going to start calling it VA. You don't want to be writing vertical asymptote every time you're doing a solution. Okay, we already looked at this. These are restrictions on the domain, i.e. the zeros of the denominator. Okay? That's what you are looking for. Vertical asymptotes, the zeros of the denominator, which are the same as the restrictions on the domain. So maybe you've highlighted this as an important thing. Vertical asymptotes, zeros of the denominator. That's all you need to know about vertical asymptotes. Okay, that one's the easiest one to come up with. Horizontal asymptotes, which, surprise, surprise, I'm going to call HA. Okay, have a little bit of a different feel to them. In order to find a horizontal asymptote, you are going to compare the degree. Do you remember what degree means? The degree is the exponent, the highest exponent on your x value. Okay, so if you have a cubic function, it's degree 3. If you have a quintic function, it's degree 5. Okay, quadratic, degree 2. So you're going to compare the degree of the numerator and the denominator. Okay, that is how you're going to find a vertical asymptote. Okay, I'm going to do this one in green. I mean a horizontal asymptote, sorry. Vertical asymptote, zeros of the denominator. Horizontal asymptote, compare the degree of the numerator and the denominator. Now there's 3 different scenarios you can encounter. The first one is that the degree, I'm going to be a bad math teacher here and say top and bottom instead of numerator and denominator just for simplicity. If the degree on top is less than the degree on the bottom, then y equals 0 is the horizontal asymptote. Okay? So let's just take a look at something sort of as an aside. This isn't really. The idea here, if you had something like x over x squared, okay? Obviously, if you use basic exponent laws, this reduces to 1 over x. Well, as the x value gets larger and larger and larger, so as it approaches infinity, 1 over a really, really big number is very, very close to 0. So that's how this gets established. If the degree on the top, so this is degree 1, is less than the degree on the bottom, which is degree 2, then this entire thing is going to approach 0. So we can write that as an asymptote. Okay, y equals 0 is the horizontal asymptote. So that's the first situation. Okay, there's only 3 situations. Either the degree on top is less, the degrees are the same, or the last situation is the degree on top is greater than the degree on the bottom. Okay? The question is, what kind of horizontal asymptote do we get when they're the same? What type of horizontal asymptote do we get when the degree on the top is greater than the degree on the bottom? Well, when they're the same, the horizontal asymptote is going to be the ratio of the leading coefficient on the top divided by the leading coefficient on the bottom. The question is, do you remember what leading coefficient on the top and leading coefficient on the bottom means? Okay, so if we look at an example of this, so degrees have to be the same. It doesn't really matter what we pick the function to be. 5x cubed minus 2x squared plus 7, I'm completely making this up, over 7x cubed plus x minus 3. So the degrees are the same. They are both degree 3. The leading coefficient is the coefficient in front of the one responsible for the degree. So in this case it's a 5. In this case it's a 7. So the horizontal asymptote would be at 5/7. Okay, so that's a line, horizontal line at 5 over 7. Okay, so if they are the same, you just look at the leading coefficient and that becomes your asymptote. Okay, so kind of want to write this here. This is going to be green. I'm always going to do them in these colors. So green is going to be your horizontal asymptote. Red is going to be our vertical asymptotes. Okay? Now the last part here, degree on the top is greater than the degree on the bottom. If that happens, we consider there to be no asymptote. Okay? So no asymptote in that case. So you're really only concerned at this point if the degree on the top is less than the degree on the bottom, or if the degree on the top is the same. When the degree on the top is greater than the degree on the bottom, this is going to bring us into a special case scenario called an oblique asymptote, which is our third type of asymptote. Okay, but for now, vertical asymptote, zeros of the denominator. Horizontal asymptote, you have to check the scenario. It's either going to be 0, it's going to be a ratio of leading coefficients, or it doesn't exist. Okay, that's so far the 2 types we have. Okay? All right. I don't know if you want to take a screenshot, copy it down. I'm setting this up in slightly different language that's in the note because you don't have someone to ask questions to, and because you don't have someone there that's maybe answering. I'm trying to maybe simplify it less than what the note is. So the note is full of sort of what I call math talk and math speak, which is fine and is necessary. But sometimes when you're alone and trying to figure this out, you need it to be simplified. So words like top and bottom instead of numerator and denominator, obviously a simple case, but same idea. I'm trying to rearrange the notes slightly so that watching the lesson isn't just me reading the note to you. It's a little bit of a different explanation. Okay, vertical, horizontal. Last one is going to be called an oblique asymptote. Okay, so this would just continue kind of on in your note. And this is all going to come together. We're going to do two really good examples. And they'll tie all this information in. Okay, so the last one, next page. The last one is called an oblique asymptote. And I'm just going to call it OA. And this occurs in a special case scenario. When the degree on top is one more than degree on the bottom. Okay, so if the degree in the numerator is one more than the degree in the denominator, this is an oblique asymptote. This is the case where we said, oh, what if the degree on the top is greater than the degree on the bottom? We said there's no vertical asymptote, or no horizontal asymptote, but there is something called an oblique asymptote. So the best way to sort of understand this is to look at an example, and this is the same example that's in the note. So we have a situation where the degree on the top, which in this case is a 3, is exactly one more than the degree on the bottom, which is a 2. Okay, so when you see this scenario, that's when you know an oblique asymptote exists. So in order to come up with what that oblique asymptote is, I'm just going to rewrite this slightly differently. So because this trinomial is being divided by a monomial, I can rewrite it as the monomial dividing individually into each part, right? That's the same thing. So 2x cubed over x squared minus x squared over x squared plus 3 over x squared. I haven't changed the question. I'm simply rewriting it so that I can see them all the quotients individually set up. So when I look at this one, you're going to use basic exponent laws from grade 9. X squared goes into x cubed, and you're just left with a single x. Obviously the 2 is there. Anything divided by itself is just 1. And then you're left over here. We can't do anything about this 3 over x squared. But what we can do is sort of think about this in a different way. We're all about extremes here, looking at what happens when something becomes very large or very small. And if we look at this scenario and imagine, again, x approaching infinity. As this approaches infinity, well, x squared is going to be approaching even quicker. This small little 3 divided by x squared, okay, so it's like 3 divided by a massive number that's approaching infinity. Well, anything divided by a massive number is something very, very small. So when you approach infinity, this little ratio here actually approaches 0. So if it's approaching 0, we can kind of disregard it. Okay, and that's what you're trying to look for. You're trying to look for, how can I simplify this? And what ends up happening is what's left here, this is simply the equation of a line, but more specifically, it's our equation of our oblique asymptote. Okay, so an oblique asymptote is an asymptote that's going on some sort of diagonal. Okay, so we looked at vertical ones, up and down ones, horizontal ones, left and right ones, and now we have an equation of a line that has a y-intercept of -1 and a slope of 2. It's going to be some sort of diagonal asymptote. Okay, so that's called an oblique asymptote, and this is the way you figure it out. The issue is, this one was very easy to divide. They aren't always easy to divide, so this is sort of a note or a warning. It's not spelled right at all. I'm going to write it in red even. Warning. Often, and when I say often, I should say basically always, have to use synthetic division. Okay, that is not going away. We learned synthetic division in chapter 3 before we even left school. we continued it in chapter 4, and lo and behold, it's coming back in chapter 5. Okay, so we have learned nothing new mathematically other than the word oblique asymptote. The word oblique is the only new thing that we have talked about. All of the math skills you already possess. Okay, so we're just going to put it all together in 2 very nice examples that are fairly lengthy, which should show you basically all the scenarios that we're going to look at and how you come up with a solution. If you follow the steps that I'm going to outline, you should not have a problem. Okay, so all that math speak is done with 2 examples, ready to go. Okay, I'm going to erase all this now. Okay. For the record, I don't like teaching like this. I'd much rather see you guys and teach in the classroom, but this is what we have. So, okay, example 1 is the scenario I just looked at. So it says, the question is just going to ask you to graph it. So the exact same question we just had, 2x cubed minus x squared plus 3 divided by x squared. Okay. The solution is going to become in 3 parts, in my opinion. Okay, it's going to be set up like this. 1, find the asymptotes, and I mean all of them. Okay, so you're going to find vertical asymptotes, horizontal asymptotes, oblique asymptotes. If they exist. They don't all exist in all situations. 2, you're going to find the intercepts. Okay, both x and y if they exist. Okay, and then 3, you're going to do the positive negative chart. And this is the key part, using, well, hold on, using vertical asymptotes and x-intercepts. So that's sort of the majority of the reasons why you have to find the asymptotes and the intercepts to begin with. Okay, so the vertical asymptotes and the x-intercepts are going to determine your ranges in your positive negative chart that we did in chapter 4. But we're going to follow these 3 steps. Okay, so step 1 is going to be asymptotes. So I'm going to sort of start a graph maybe on the bottom here. It's the best spot to do it. I don't need to put numbers on it yet. But as I go, I'd rather just start kind of the sketch as I go. And if I have to go up here and finish the question, that's fine. So in step 1, when you're coming up with asymptotes, you really want to do all of them. Okay, so start in the order we learned them. We're going to do the vertical asymptote first, and then from there we can get horizontal and oblique. So if you remember, the vertical asymptote is looking at restrictions on the domain. So you're basically saying, what values make the domain 0? Okay, so in this case, if you actually looked at the domain, x belongs to real numbers, such that x, what's the only restriction on x squared? Can't be 0. Okay, so when you're graphing that, and remember I said I will do vertical asymptotes in red, that just means that you have a vertical asymptote up and down right on the axis at x equals 0. Okay, that's the only one exists because in this one we have a pretty simplified denominator, right? Simply x squared. Okay, that takes care of the vertical asymptote. The horizontal asymptote, which I said I would do in green, okay? The horizontal asymptote, we have to look at the scenario of the coefficients, of the degrees. So here we look, this is degree 3 polynomial, this is a degree 2 polynomial. So this is a situation where the degree on the top is more than the degree on the bottom. So we look and we say, well, degree 3 is greater than degree 2, therefore no horizontal asymptotes. Okay, that was case 3 of the horizontal asymptote case. Okay, sorry, this is still step 1. The last one we want to do is oblique asymptotes. I'm going to do the oblique asymptote in, I don't know, what other color do I have? Blue. Oblique asymptotes I'll do in blue, And this is the question I just did on the previous slide. So we did this and we found that the oblique asymptote was 2x minus 1. Okay, so that's the idea that you're actually dividing it in. So when you divide the x squared in, it's oblique asymptotes exist if the degree on the numerator is exactly 1 more than the degree on the denominator. Divide it in, get a 2. Divide it in, get a negative 1. Divide it in here, it approaches 0. So this is our oblique asymptote. So in order to graph this, I should put some dashes on at least. 1, 2, 3, 4. I don't need to put numbers. You guys know what a graph looks like. It's just a sketch at this point. Okay, so in order to graph this, use grade 9 methods. That's a y-intercept of negative 1. I put it there. And it goes, graph it on. Slope of 2 means you go up 2 over 1, up 2 over 1. And now you have, like we said before, a diagonal line. Okay, that goes through there. So that's going to be your oblique asymptote. So in this scenario, we have no horizontal ones. We have a vertical asymptote. We have an oblique asymptote. That is step 1. Check. Done. Step 2 are the intercepts. So in this case, we want to find x and y intercepts. So to get an x-intercept, let y, or in this case, well, it is y, let y equal 0. Okay, so when I do that, I get 0 equals 2x cubed minus x squared plus 3 over x squared. Well, how will I solve this? Well, I'm going to multiply both sides by x squared. What happens when I multiply x squared by 0? It stays 0. So all you're left with is this. Well, now, in order to find the zeros of this, I have to factor it. Well, it's not easy to factor. It's cubic, which means I can't use factoring from grade 10. I can't use factoring from grade 11. I have to use factoring from grade 12, which means we have to use synthetic division. So you're looking at this little thing, I don't know, call it something else, g of x. And at this point, this should be fairly straightforward. You're trying to find a value of x that makes this go to 0. Okay, so because I've already done this, I know it's negative 1. It becomes 0. I start up my synthetic division. I put a 1 here, sorry, a negative 1 there. I put in the coefficients. Coefficient of x cubed is 2. X squared, negative 1. There is no x value. I better put a 0 there. Constant, 3. Do my synthetic division. So remember, you're dropping the 2 down. This shouldn't need any lesson anymore. I think synthetic division is something we know how to do. Add, multiply, add, multiply. Remainder 0 is our main goal. So we now have, I guess I'm going to have to go up. No, I think I can do it down here. Where's my eraser? The graph doesn't need to go this far, so I can continue down here. So now we have two things. We have x plus 1, and we have 2x squared minus 3x plus 3. Okay, well, now that's factorable. When I look at this, I shouldn't say it's factorable. When I look at this, and I think, well, how am I going to factor that? Many of you will attempt to use just regular methods. It's a complex trinomial, and you're going to have trouble finding some. If you attempt to put it into the quadratic formula, you're going to get no solution, because when you try to take the discriminant, so the square root of b squared minus 4ac, it's going to pop out a negative. So this part here actually has no roots. Now, you're at a bit of an advantage because you can pump this into a computer or a calculator, or whatever you happen to have, seeing as you're at home, and it'll tell you there's no roots for that part. So the only one that we really have is that x equals negative 1. So we're really looking at the only x-intercept we have is negative 1, 0. So we're looking at a point. I guess I can do it in, I'm going to do it in green. Negative 1, 0. This is our x-intercept right here. Okay. So we do not have another one because there were no roots coming off of that. All right. Okay, so that takes care of the x-intercept. You want to do the same thing with the y-intercept. In this case, you're letting x equal 0. Well, when I let x equal 0 here, I get a denominator of 0. Am I allowed to divide by 0? No. Okay, so this one does not exist. There is no y-intercept. We cannot do it. Okay, so does not exist, we don't worry about it. That takes care of step 2. The part you're going to be doing synthetic division is always finding the intercepts. So just be aware. The synthetic division is going to happen for you, and it's going to happen in that step. Okay, the last step, step 3, is coming up with the positive-negative chart. And what I said here is you're going to use vertical asymptotes and x-intercepts. So we have one vertical asymptote, we have one x-intercept. Our x-intercept is at -1, our asymptote is at 0. So those are the ranges we're going to do. So when we set up our chart, we're going to look here and say the first sort of column will be x is less than -1. That's the first one we come upon from the left. Then it's going to be between -1 and 0. That's the next one, and then greater than 0. Those are the only ranges we have here. Now, in terms of how you set up your chart, I don't know. Some people like to just stick to the numerator and the denominator and then look at the quotient. So, or some people just want to do it all in one step. That's fine. 2x cubed minus x squared plus 3. That's the numerator. The denominator, in this case, x squared. So the one you're concerned about is the quotient. What happens when you divide them? Okay, so you're really just, again, you know how to use this chart already. You are picking a value less than -1. So it doesn't matter what you pick. You could pick -5. When you substitute it in here, you're going to realize that pops out a negative. X squared, it doesn't matter what value you pick. It doesn't matter if it's a negative. Doesn't matter if it's a positive. Anything squared pops out a positive. So I know all the way across here, the x squared is going to be a positive. So it's just a matter of picking a number in each range, subbing it into the numerator, and seeing what happens. So here I have to pick a number between -1 and 0. So you pick -1/2, put it in, and you realize it's going to be positive. A number greater than 0, something like 1, you realize it's going to be positive. Now to do the quotient, you simply divide. A negative divided by a positive is negative. Positive divided by positive, positive. Positive divided by positive, positive. And remember, this is the part you care about. So what this is saying, and I'm going to graph it in green, this is really the part of the question that we've been looking for, is when x is less than -1. Remember, these asymptotes, you always approach the asymptotes. That's what they're there for. So these asymptotes act as a guide for where our graph is going to go. Okay? But it's just a matter of where is it turning and what part of the asymptote is it approaching. Well, that's what this chart tells you. If you are less than -1, so we're talking about this part, okay? It has to be in the negative section, which means we're down here. We're not up here. On this side of the green dot, on this side of -1, we have to be negative, which means we're approaching the blue asymptote here. When we're between -1 and 0, so between this green dot and the red line, okay, we have to be in the positive portion. In the positive portion, the way that we are going to approach that vertical asymptote. Okay, so that's part of my graph. Now when we flip into the other side, x is greater than 0, whoa, here's a little bit of a mess because there's this section in here we could go. There's this section over here. There's this section over here. It tells us when we are greater than 0, we have to be in the positive part of the graph. Okay, so greater than 0, positive part. We have to approach both asymptotes, so we're somehow kind of swinging around in both directions. Okay, there's no other point here, so we don't touch that area. There's no other asymptote. There's no other x-intercept, so we're not going in that area at all. So in reality, this green graph here is our y equals 2x cubed minus x squared plus 3 over x squared. Okay? Is it a lot of work? Maybe. Is it something you can handle? For sure. Okay? Stick to these things. Find the asymptotes first. Check all 3 types. Find the intercepts, x and y. You may have to use synthetic division. By may, I mean almost 100% yes. Post those. Once you look at your x-intercepts and your vertical asymptotes, set up the ranges of values to see whether the graph is in the positive or the negative area, and then simply sketch your outcome. Okay? Follow these 3 steps every single time. You will not have a problem. If you knew how to do chapter 3 and chapter 4, this should not be an issue. Okay, I'll do the last example just to make sure we cover it all. the more examples, the better, really. I know it takes a long time. It takes a long time for me to go over. It takes a long time for me to attempt to teach in one swoop without making a mistake. Okay, so this example, in my opinion, an even better one. Okay, so number 2 says f of x equals x squared in the numerator divided by x cubed minus 2x squared minus 5x plus 6. Make sure I get that right. Okay, so step 1, asymptotes. Vertical asymptotes occur when? Where the denominator equals 0. Oh, we got a very big denominator here. So the vertical asymptote occurs when this equals 0. Well, the only way we can find out where this equals 0 is to factor it. Okay, so again, when you set this up, you're kind of saying, well, I'm not going to call it f of x because f of x is this whole thing. So the bottom is just going to be called g of x right now. I want to find out where the denominator equals 0. That will give me my things. Well, I'm not going to be able to find that out unless I factor this. How do you factor it? Do synthetic division. So you're trying to find out what value of x makes this 0. I already did it, so I know it's 1. So therefore, x minus 1 is a factor. Okay, we all start to know that. Set up your synthetic division. I put my 1 in, then I put my coefficients 1, negative 2, negative 5, and 6. And again, follow synthetic division. Not a problem. Be happy they're only cubic. Just makes your life a little bit easier. It's one less step. Negative 1, negative 6, negative 6. Good. Remainder is 0. So I now have this. X minus 1, x squared minus x minus 6. And lo and behold, you look at this and you say, well, is this easy to factor? Thank goodness, yes. Two numbers that multiply to negative 6 add to negative 1, negative 3, and positive 2. So what this tells us is we have vertical asymptotes at x equals 1, x equals 3, and x equals negative 2. Those are all vertical asymptotes. So I'm going to set up my little graph right here. Because again, as soon as I see where it is, I don't want to wait till the end. I want to put my asymptotes on right now. So 1, 2, 3, 4, 5. So I found out I have an asymptote at 1. Let me at least put some numbers on here. 2, 4. Make it look like I'm an official teacher. Okay. So we have asymptotes at x equals 1. Vertical. Up and down. Ding, 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 ding. Done. X equals 3. And x equals negative 2. Woo! See, things are going to start getting interesting now. We already have 3 vertical asymptotes on. We have to look at the next one. It's going to be horizontal asymptotes. So horizontal asymptotes, you may remember, is talking about the degree. So we look at the degree. Degree 2 is less than degree 3. What do we do in that situation when the degrees are less? If the degree on the top is less than the degree on the bottom, y equals 0 is your asymptote. So I now have to go across the axis, and I have, for the first time in an example, a horizontal asymptote. So I now have 1 horizontal asymptote, 3 vertical asymptotes, and in terms of an oblique asymptote, we already know there's not going to be one because this degree was smaller than this degree. Oblique asymptotes only occur if the numerator's degree is 1 more than the denominator. So if you want to write oblique asymptote, does not exist. If you're just trying to write down what's going on, it does not exist. Okay. Step 2 means can we get intercepts? Okay, so again, x-intercept, the way you're going to find that, let y equal 0. Well, if I let y equal 0 here, 0 equals, what happens every time to the denominator? Has to get multiplied up, right? When it gets multiplied up, it gets eaten by the 0. Anything multiplied by 0 is 0. And we are simply left with x equaling 0. So we now know we have a 0 at an intercept, x-intercept at x equals 0, y equals 0. So I'll just throw that on there. Add to our issues. Horizontal asymptote, 3 vertical, 1 x-intercept. You can do the same thing and check your y-intercepts. I'm going to do it down here because I already know it's going to be simple. Y-intercept means let x equal 0. Put a 0 in for this, it goes away. Goes away, goes away, goes away. Those all become 0. All you're left with is a 6 in the bottom. Well, what's 0 divided by 6? 0. So this ended up giving us the exact same intercept, 0, 0. You don't need to graph the same point twice, so that's no problem. Now, step 3, and the most exciting part, setting up the chart with the intervals. The intervals have to come from vertical asymptotes and x-intercepts. Okay, make sure you know that. So this one we have 1, 2, 3, 4 areas, which mean we will have 5 intervals. The first interval, you start from the left, is going to be x less than -2. The next interval is going to be between the vertical asymptote and the next thing it hits, which in this case is an x-intercept. -2 is less than x is less than 0. Then 0 to 1. Then 1 to 3. And then the last one, x greater than 3. Okay, sorry, it had to be small, but 5 intervals. And again, it's sort of up to you how you do this. Some people like to do it all in one step. Oops. I personally want to make it easier for you guys. I think if you set it up, this is the quotient, that's the one you're interested in. Numerator, x squared. Denominator, if you have it in factored form already, use it. Why would we plug it into there when we can plug it into this easier version, right? So we have x minus 1, x minus 3, x plus 2. Okay, so you're going to go through and simply look. Again, the x squared is our friend. Anything squared, whether it's negative, whether it's positive, is going to pop out a positive answer. So I know everything across x squared is positive. The numerator is positive no matter what. You're going to have to check when you put in the values in each of these ranges into the denominator. So when I pick something less than -2, something like -3, negative, positive. So this is going to pop out a negative, right? Yeah, negative. It's going to pop out a negative. I go across and do the same sort of thing. You're going to have to trust me. And then again, the big thing you're doing is saying, well, if this is a quotient, I need to divide a positive and a negative. I get a negative, a positive, a negative, a positive. Okay, well, this is going to help us in our graphing. Because now we look at each of these things. We have to be very cognizant of all these asymptotes. Our graph always approaches the asymptotes. We just have to find out where. So when it's less than -2, we have 2 options. There's something splitting us right between positive and negative. So we're going to be on one of those sides. We look, x less than -2 is going to be in the negative area. Being in the negative area, but it's got to approach our vertical asymptote and it's got to approach our horizontal asymptote. So it's going to end up there. When we go between -2 and 0, okay, so that's just between this red line and the blue dot, we're in the positive section. We have to hit the blue dot and we have to approach the asymptote, but only in the positive area. Okay, when I go across over here between 0 and 1, I still have to hit the blue dot. It's just a matter of, am I coming down here to the negatives, kind of like a cubic sort of shape, or am I coming back up? Well, sure enough, we're coming back up. We have to stay in positive, but again, we have to approach the asymptote, so it looks more like a quadratic-y shape in that section. Then I go between 1 and 3, and I have to be in the negative. Well, I have to be in the negative for both of these. Well, how do I approach both of these asymptotes from the negative? Well, somehow you have to turn around. Still in this section, I approach all 3 asymptotes. Okay, so it doesn't touch the green one, doesn't touch the red ones, but it's really approaching both. And then over here, greater than 3, I'm either going to be down here in the boomerang type shape, or I'm going to be up there. Sure enough, I'm at the top, and I go across like that. Okay, you always have to approach all of your asymptotes, so be aware. That's what an asymptote is. It means the graph is approaching it. So this blue line, all these blue lines, the combination of them is this function. Okay? I hope it's clear-ish. Okay, if you're struggling, set it up in the way 1, 2, 3 steps. All the asymptotes, check them all, see where they exist. Draw them right away so you know. Check the intercepts, x and y. Graph them. Then make your chart based on vertical asymptotes, x-intercepts. The number of vertical asymptotes and x-intercepts, whatever that number is, you're going to have one more interval than the number of vertical asymptotes and x-intercepts you have. So just be aware. Okay, 5.2 when we do it in class is a 2-day lesson. So don't be too hard on yourself if you can't get a lot of it done at once. Take a couple days and then move on to 5.3. Okay, another one bites the dust. Oh, my legs. Oh. Getting old sucks.